let's get into the KSP stuff. And I want to review solubility, which is a Chem 101 thing. So in Chem 101, you should have got these solubility rules, right? So these solubility rules are how you determined whether or not an ionic compound, a salt, was going to dissolve in water. um, and I don't know if your Chem 101 professor made you memorize it or not, but it's like nitrate salts are soluble, nitrate and acetate salts are soluble, uh, ammonium and chloride, bromide, iodide salts are soluble, so like an alkali earth metal and ammonium salts are soluble. Then we've got chloride, bromide, iodide salts are soluble, and then we run into some exceptions. So if the chloride is paired with silver or lead 2 or mercury 1, that would be insoluble. Then we got sulfate salts are soluble unless that sulfate's paired with strontium, barium, lead, silver, or calcium. Then you got hydroxide salts are insoluble. Carbonate, phosphate, chromate, all those salts are insoluble as well. The rules are kind of ranked in order of importance. So as soon as you kind of find a rule that applies, you stop reading because like sometimes they would contradict each other. So we had in Chem 101, again, this should look familiar. In Chem 101, we had a really elementary discussion of solubility, right? Where we had these rules. But solubility is a more complex phenomena that you were not ready to discuss in 101 because you had not written mass action equilibria expressions. But now that we know how to write equilibria expressions, what we need to talk about is the fact that solubility is really a continuum, right? Where you have, 100% soluble, and then you have 100% insoluble, right? And, you got the extremes of both. So something that completely dissolves, something that does not dissolve at all, and then you got everything in the middle, right? So for example, silver iodide is insoluble. But how insoluble? Is it like 98% insoluble? Does 2% of it dissolve? How much is going to dissolve here? So that's what we're looking at in Chem 102. In Chem 102, we're going to look at these insoluble salts, these salts that don't dissolve very much. And we're actually going to try to use equilibria to determine how much these rather insoluble salts actually do dissolve. You may have heard water be called the universal solvent, and that's because water is really good at dissolving everything, right? I mean, there are those studies now that say the microplastics that are in our blood and stuff, right? So from drinking out of all these plastic bottles, and I still do it, it hasn't scared me yet, but from drinking out of all these plastic bottles and stuff, all the microplastics that are now in our bloodstream and stuff, uh, it's crazy. So water is even dissolving plastics. So water is incredible with its ability to dissolve stuff. It's just so polar. It's just really great solvent. Um, and we are going to focus on now, these things that are insoluble. How much do they actually dissolve though? What's the actual amount that we get? So here's how we do that. Here is a insoluble compound, calcium fluoride. So it's a solid. And what we do is we set this up like it's an equilibria problem where we say, okay, calcium fluoride, a little bit of it's going to dissolve, but most of it stays together as the solid. But if it does dissolve, what's it going to break up into? And this is a dissociation equation. So calcium fluoride, if it were to dissolve, would break up into a calcium plus 2 cation and 2 fluoride ions. So the first thing you have to do is be able to write a balanced dissociation equation for a salt. Okay, and the key here is that these are heterogeneous equilibria. Okay, what does heterogeneous equilibria mean? That means that we have something that's not aqueous or gaseous. We have a solid or a liquid. And hopefully you remember that pure solids and pure liquids are not included in mass action expressions because you got to remember these mass action expressions have brackets, which means molarity. So if you're a pure solid or pure liquid, then you don't have a concentration, right? Like there's no, because it's moles per liter. But if you're a solid, moles per liter of what? Or if you're a pure liquid, moles. So you're only aqueous and gaseous things go into mass action expressions. So the key to these solubility equilibria expressions is that we leave the solid out. Now remember, it's products over reactants. So these products go in the numerator. My reactant's a solid, so my denominator is 1. So we just end up with something like this. This would be the mass action expression for this solid calcium fluoride dissolving in water. Okay, where we have the calcium ion concentration times the fluoride ion concentration. And remember, the coefficient becomes the exponent. So then that ends up getting squared. Okay. Um, let's see. So this is absolutely an equilibrium constant, so KEQ or KC. But because this is a constant for solubility, we call it KSP, okay? And it stands for solubility product constant. So these are equilibrium constants for dissociation of an insoluble substance in water, or a relatively insoluble substance in water. And again, instead of just calling it KEQ or KC, we now call it a KSP, which stands for solubility product constant. Okay. Boy, let's kind of work through one of these. We're going to do ice tables. So this is ice tables again, because these are equilibrium problems. But these are not nearly as bad as, the stuff we were doing. Okay. It's actually like a little easier. So here is our goal. I would like to figure out what's the solubility of silver chloride. So what is the molar solubility of silver chloride? How much silver chloride will actually dissolve in pure water? Okay, if the solubility product constant for silver chloride is 1.77 times 10 to the negative 10th. Now you'll notice these KSP values are almost always ridiculously small. Why are they ridiculously small? Because these are insoluble, like they don't want to dissolve. The reactant side is heavily favored. These are mostly going to stay together. We're just trying to figure out what's the little bit that it actually does break apart. So if you give me a second to copy some of this onto the board, I will, and then I'll make it full screen. Really, the only difference with KSP problems is we use an S for solubility instead of an X. So we're still going to make an ice table. Now, here's the key. Okay, before we get ahead of ourselves, let's write that mass action expression for this. So I want to write the mass action expression for this salt. So it's going to be KSP equals products over reactants. So the concentration of silver ions times the concentration of chloride ions over, remember that's a solid, so it doesn't go in there, so it's over 1, which means you don't really have to write that. Now, these all have coefficients of 1, so it's all to the first power. This one's going to be super duper duper easy. Now we're going to make our ice table, but here's the key. Your ice table only has a row for the things that are in the mass action expression. So what does that mean? You are not going to have 3 rows. The solid does not go into the ice table. So you're only going to have 2 rows in this ice table. So I, C, E. We're going to make a table with 2 rows. We're going to have a silver cation and a chloride anion, and there's our ice table. So if you want to make a note of that, only things in the mass action expression get to go into the ice table here. Only things in the mass action expression go into the ice table. Okay, so let's imagine what we're doing here. We have a beaker of distilled water, and we're going to drop this rather insoluble silver chloride into the water. So the first thing, the I column, is for initial. So what is the initial amount of silver ions in here and the initial amount of chloride ions in here? Well, because this was distilled water, the initial amount of silver and the initial amount of chloride is 0. Now I'm going to drop this in, and some of it's going to dissolve. Okay, not much, but some. So what is my change going to be? Well, my silver, so some of it's going to dissolve. My silver, this is where before we would have written plus X. The silver would go up by plus X, and the chloride would go up by plus X. Now, you can still use X's if you want, but technically for solubility, it is encouraged that you use an S. So it's going to go up by S. We're calling it S now, some amount S. If there was a 2 here, this would go up by 2S. So it's the same thing. So now at equilibrium is going to be 0 plus S, so that's S. And at equilibrium, this is going to be 0 plus S, which is S. So now what do we do? Well, now we do the same thing we've been doing with all this ice table stuff. We're now going to take these values, plug them in here, and solve for S. So here we go. The Ksp is 1.77 times 10 to the negative 10, and that equals S times S. So this becomes 1.77 times 10 to the negative 10. That equals S squared. And now we can take the square root, and we'll get the solubility here. So that would be the square root of 1.77 times 10 to the negative 10. And I get S equals 1.33 times 10 to the negative 5th. Now, what are the units on this? The units on this are going to be molarity. Okay? Because this is a concentration. So what's the solubility? How much is going to dissolve? What is the molarity of this going to be? Okay? And it's going to be 1.33 times 10 to the negative 5th molar. That is our solubility. So the answer is, yeah, silver chloride's pretty darn insoluble, right? If I drop silver chloride in water, and I have an entire liter of water, then there's only going to be 1.33 times 10 to the negative 5th moles. So 0.0000133 moles of silver chloride in that entire liter. Not very much at all. Okay, so it is rather insoluble. We were correct. So there's the answer. The solubility is 1.33 times 10 to the negative 5th molar. Awesome. So now what I want to do is what's called a common ion problem. And this is really a manifestation of Le Chatelier's principle. Now what we want to do is dissolve it in a sodium chloride solution. And I want to talk about what that's going to do. So before we do the math, let's look at this through an equilibrium lens with like Le Chatelier. So now, instead of dissolving the silver chloride in pure distilled water, now we're going to dissolve it in a saline solution. And this is what we're eventually going to do 2 weeks or a week from this Wednesday. So a week and a half from now, when we get to our KSP lab, we will be doing this. We're going to dissolve a compound in pure water, and then we're going to dissolve a compound in a solution that has a common ion. So this is called a common ion problem. Here's why it's a common ion. Sodium chloride has chloride, and my salt, when it dissolves, has chloride. So what are we doing here? Well, if we look at this through a Le Chatelier lens, we've added chloride. And when you add something, according to Le Chatelier, the equilibrium position shifts away. So I'm adding chloride, the equilibrium shifts away. Do you think that this silver chloride is going to dissolve more or less with a common ion in there? What do we think? It's going to dissolve less, right? It's going to stay together more, right? So this is the common ion effect, where if I have a common ion dissolved in here, it's really Le Chatelier's principle, the solute will dissolve even less. So we should have a lower solubility for silver chloride in the sodium chloride solution than in pure water, right? It should be that we're actually going to calculate what it is and we're going to compare. So in pure water, the solubility was 1.33 times 10 to the negative 5th. Now I want to get it in the sodium chloride. How is this really going to what's this really going to change? Well, when we make our ice table, we now have an initial concentration of chloride ions. So if I go back to the slide, I believe it was 0.1 molar sodium chloride. So it's 0.100 molar sodium chloride. So this is 0.100 molar in sodium chloride. Now I want to make my ice. So first of all, we can write our mass action expression again. So Ksp equals the silver ion concentration times the chloride ion concentration. Now we can make our ice table. Remember, you only have the number of rows in your ice table that is equal to the number of things in your mass action expression. So we have a row for silver and a row for chloride. Now, there is no silver in here initially, so that is a 0. But we do have an initial amount of chloride. It is 0.100 molar in chloride. When this dissolves, the silver still goes up by some amount S, and the chloride still goes up by some amount S. But now what's different is my E column for the chloride is now 0.100 plus S, because I had an initial chloride ion concentration in there. I had a common ion. So now we plug it and chug it. So Ksp 1.77 times 10 to the negative 10. That equals S times 0.100 plus S. Now, we need to talk. So first of all, let's pause there. Anybody have any questions on the ice table? We're getting to this point. Does everybody see how this is now different? Because I have an initial concentration of one of the things my salt is dissociating into. Okay, cool. If we just do math with this, we're going to have a problem. If we just do good old-fashioned algebra 2, when I distribute that, I'm going to end up with a quadratic. Then that's going to suck, right? Quadratic formula. So to avoid the quadratic, what could we try to do from the last unit? How do we sometimes avoid the quadratic?
You can see if X is small. You can see if X is small.
That's right. Thank you, Laura. We do X is small. Thank you, Maggie. Absolutely. Only this time it's S is small, right? So instead of X, now it's S, right? So we need to see if S is small. If S is small, we can get rid of the plus S, just like with the X, right? So we take our smallest initial concentration, 0.100. We divide it by the constant, 1.77 times 10 to the negative 10th. And oh, yeah, baby. That's greater than 500. S is small. So you can get rid of that plus S. So now it's 0.1. So what does this reduce down to? I'm going to go down here, folks. So sorry. I kind of should have wrote that over here, and my beaker was in the way. So we're going to get down to 1.77 times 10 to the negative 10th equals 0.100 S. Divide both sides by 0.100. So times 10 to the negative 11th. Or does it go to the negative 9th? I know, I just forget. Negative 9th. Of course, it's going to get bigger. Don't divide by. So 1.77 times 10 to the negative 9th molar. I'm going to get a new marker here in a second. Let's see if our guess was correct. We said with a common ion, according to Le Chatelier's principle, it should be less soluble. And oh yeah, in pure water, the solubility was 1.33 times 10 to the negative 5th. But now with the common ion, the solubility drops to times 10 to the negative 9th, right? It's almost half as soluble, okay? Way less soluble. Here's a graph. It's kind of showing that kind of thing. So here's the solubility of magnesium fluoride with no common ion. So this is in pure water. And you can see it's actually decently soluble as far as insoluble things go, if that makes any sense. It's like an oxymoron, but it's times 10 to like the negative 3rd. Look what happens as I dissolve more sodium fluoride, because the sodium fluoride has a common fluoride ion, right? So it's got a common ion. So as the fluoride ion concentration increases, man, does that solubility drop off. You get to 0.12 molar in fluoride, and you're down to like times 10 to the negative 9th, and solubility really, really, really drops off. Don't worry about that one. If I had more time, I'd talk about that, but we don't need to worry about pH effects and all that stuff. Okay, so I want to do a more difficult one. I want to get the solubility of lead-2 chloride in pure water. Here's what I need you to do. I need you to write a dissociation equation for lead-2 chloride. I need you to write a mass action expression. Then I want you to try to make an ice table. The worst thing could happen is you get it wrong and we fix it. So I want you to try. This one is a little trickier, I'll warn you. Let's see if you can get the first step. Write the dissociation equation, Next step, mass action expression. Third step, ice table. Give it a shot. I'm going to try to find a different marker. All right, see how this went. The first step is you got to write a balanced association equation. You get this wrong, everything else is going to be wrong. So no pressure. This is going to break apart into the lead plus 2 cation and 2 chloride ions. People miss that too. That's got to come out in front. That's going to jack the whole thing up. Now we need to write our mass action expression, Ksp equals the lead plus 2 ion times the chloride ion, and then that gets squared. So there's our mass action expression for this. Remember, the solid does not go in. How we doing? Now it's ice table time. So ICE, only 2 rows. We got a row for the lead ion, and we got a row for the chloride ion. This is in pure water, so there is no initial lead or chloride ion concentration. And now here's it's going to be a little different. When this dissolves, the amount of lead is going to go up by 1s, but the amount of chloride is going to go up by 2s. So now this is s, and that is 2s. And now we go to plug this in. 1.17 times 10 to the negative fifth equals s times the quantity 2s squared. I'm going to pause there because then we got to talk. We're going to have to look for a button or a calculator here. All right. First thing, very important you put these parentheses here. Because if you don't put those parentheses there, you're going to forget to square the 2. So what this is, this becomes 1.17 times 10 to the negative fifth. That equals s times 4s squared. And then I multiply by s, that becomes 1.17 times 10 to the negative fifth equals 4s cubed. Now I need to solve for s. How are we going to do that? Divide both sides by 4. So 1.17 e negative 5 divided by 4. That's 2.925. We'll round at the end. Times 10 to the negative 6 equals s cubed. And now, how do we get s? Well, I need to take the cubed root. So I need to do the cubed root. Now, I know what you're saying. Where is the cubed root button on my calculator? Well, if you got a TI-84 or a TI-83, you are in luck because I can show you that button, ladies and gentlemen. You're going to hit the math button. The math button is right here under alpha. Hit that math button, then you get a menu going to pop up like that. And if you look, the fourth option is the cubed root button. Now, before you hit that, I want you to look at the fifth option because we gonna need that fifth option here momentarily. We get into some crazier salts. That fifth option is the X root button. So if you need to take a fourth root or a fifth root or a sixth root or something, you're gonna have to type in the 6 beforehand and then the X root. So for example, if I wanted to take the fifth root of something, I would type a 5 in first. So I'd type a 5 in. Then I would go math, and I would do that X root thing. So I hit the fifth button, do that X root. So now I'm taking the fifth root, and I don't know, fifth root of 125 or something. Fifth root of 125, 2.6. So that's how you take like a fifth root. Anyway, we don't need that. You use the cube root button. So math, and then you hit the 4. We're going to hit the 4 to get the cubed root, or you can type a 3 in and do the X root. You do you. Now we're going to type that in there. 2.925 e negative 6. The cubed root of that is 0.0143. 0.0143. So the solubility is 0.0143 molar. Now I believe it just asked for the solubility. S stands for solubility. You would be done. What is the solubility? Now, if it said, what is the lead 2 ion concentration, well, that is S. It would be that. Now, if it said, what is the chloride ion concentration? The chloride ion concentration, excuse me, the chloride ion concentration is 2 times S. So it's 2 times that, if that makes sense to you. In this problem, I'm giving you the solubility. So I'm telling you S. The solubility of silver 2 sulfate in pure water is 1.2 times 10 to the negative fifth molar. What is the Ksp? So you're kind of working backwards, although these problems are all the same, whether you're solving for S or Ksp. Okay, here's what I need you to do. You need to write a balanced dissociation equation for silver sulfate. You need to write a mass action expression. You need to make an ice table, and then you got it, and then we'll talk. Okay, so see if you can't go ahead and get started. This one's a little different. I'm giving you S and asking for Ksp. All right, let's do it. Here we go. So this is going to dissolve into 2 silver cations and a sulfate anion. And now we can write our mass action expression. It's going to be the silver ion concentration squared times the sulfate ion concentration. Just like that. And now we can make our ice table. Now the initial amount of silver sulfate, this was in distilled water, 0. The silver goes up by 2S, and the sulfate just goes up by S. We can plug this in. Ksp equals 2S squared times S. Ksp equals 4S squared times S. Ksp equals 4S cubed. So we end up with a very similar end result to that last problem. Now here's where this one's slightly different. Only place it's different is at the very end. This time, I'm giving you S and you're solving for Ksp. So this becomes Ksp equals 4 times 1.2 times 10 to the negative fifth cubed. So remember, please excuse my dear Aunt Sally, your calculator will probably do it right, but you want to cube it before you multiply by 4. Here we go. I get a Ksp, a solubility product constant for silver sulfate. I get 6.91 times 10 to the negative 15th. Looks like 2 sig fig, so how about 6.9 times 10 to the negative 15th as our solubility product constant for silver sulfate?